So, welcome everyone. My name is Berk. I'm the chief architect for security at Riverbed. I think this is my third time with you guys presenting, and this is the first time we're obviously doing it from home. And I regret that because one thing I noticed is that Riverbed absolutely buys the best snacks in the conference room when you guys all visit. And so next time, let's make sure we do this again in San Francisco. So I'm going to be taking you through a number of different sessions on advanced analytics, AIOps, machine learning, and various techniques that we already use and that we plan to use in the near future to make this process of network troubleshooting, application troubleshooting go smoother. Now, the question you might ask is, why is this security guy doing that story? And that's actually interesting, and I'll give you that background. I years and years ago, longer ago than I'm willing to admit to, got a PhD in machine learning and AI. And this was in a time when machine learning and AI was absolutely not yet cool. And I obviously went into the cybersecurity industry. I spent decades there, mostly applying things I'd learned in school. And then I joined Riverbed through acquisition, and it was pretty obvious to me that, and that's now a few years back, that we have all these fantastic data sources. We're grabbing data from all over the network. We're grabbing data on hosts. We can even grab packets on host-based agents. It's like there's no end to the telemetry. And then I go onto the dashboards that Gwen is going to show you later. And what I see is that, okay, well, we're going to plot all of it. And then there's a strip chart of that and a top end list of that. And I'm like, well, people are still going through this manually one by one, wrenching, right, their way to the answer that they need. And I'm like, we can do better than that. So I spun up a group within Riverbed that specifically focuses on using this data. And what I'm gonna do today is I'm gonna give you some background on AI and ML, try to demystify it a bit. And this will be very academic. Then I'm going to show you a couple of things where we're simply applying it to our data. Now, I'm gonna end the session. The last thing I'll do today is talk about how that is, why it is specifically hard to do in computer networks, right? And this is something that a lot of people talk about. I felt like I actually want to end on that low note. So it's going to be an inverted talk, if you will. So my first session is on how do we get from wrenching to conducting. And I'm going to tell you at the end what I mean by that. So easy enough. If you have a lot of data, then let's train a neural network. Let's use some AI, right? Let's do that because it'll make it better. And that's pretty much what all the marketing is telling you all over the industry. But let's take a look at what we really mean by the words intelligence. Now, and these definitions come, actually, this is interesting enough, these come from a conference that was originally held 55, almost 60 years ago at Dartmouth College in New Hampshire, where everyone who knew anything about this new field of AI got together to try to define it. And they simply said, like, look, if we can simulate in a computer what the human brain is doing, well, then we can effectively build a computer program that's just as intelligent as a human is, right? And so the question became, well, what is intelligent? And here's some of these things, and none of this should particularly surprise you. But for instance, have significant recall of events, right? Things you remember stuff. In networking, this is often called tribal knowledge, right? Like we remember, configurations and things that happened and how that impacted performance. You need to be creative about answering things about situations you've never seen before, even if those situations are very complex, right? You can speak languages, multiple of them, right? And you can generalize. And that's really where this thing comes down to. It's sort of, a computer program that just repeats what it has seen before isn't always as useful as one that can see a situation and based on prior experiences and the new information can do something novel that it has never done before. So these are sort of some definitions, but what it really comes down to from a science perspective is, given a situation represented by data, what is the best possible action we can take Now, with data here, I don't just mean like the stuff that we have collected, right? Like if you think about autonomous driving of a car, there's obviously the inputs from the cameras, there's the inputs from the speed sensors, and whatever else drives a car. But there's also sort of an internal state model, right? Like you have represented the 3D environment around you, and you have gotten you can reason about it. So you're using some internal data, some external data to try to come to some conclusion. So the very first way in which we go about that, at least in the early days, was, well, look, if there are experts available for a field, then let's figure out how an expert handles decision making, right? Taking the best action given the circumstances, and encode that in a knowledge base. Then all these rules go into this knowledge base, and we used to encode those in Lisp for those of you that still remember those days. And then we'll build an inference engine that can take some of these rules, that can use some rules and take some of these pieces of encoded knowledge to come up with the best action, and then communicate that to a non-expert user through a user interface. And if we do that, we've encoded artificial intelligence. Well, there's a lot of problems with that, besides the fact that nobody on this call today likes Lisp very much. Be careful what I say. But first of all, experts may not exist for the problem space. We know that in networking, we find novel problems all the time that we've never seen before, because networks are built to fit your particular operation, right? Networks are a little bit like brick and mortar. You can build a hospital with brick and mortar, and you can build a prison with brick and mortar, and you can build a school with brick and mortar. And depending on what the function is, you're going to use that brick and mortar in a slightly different way, and you better not confuse the two, right? Other issues that we suffer are that experts sometimes are unable to articulate their diagnostic rules. And this is like when you go to the car mechanic, you describe 3 things that are wrong with your car, and without the guy even hooking up diagnostic tools or looking at us, it's like, you know what? I bet it's this. And that's part of like tribal knowledge, part of sort of gut feel, and that's not encodable, at least not in rules. Then one of the other things that really plagued us in artificial intelligence always was the fact that large rule bases tend to be really, really hard to manage. Like rules obscure other rules, not the right rule is used, right? We forget to take out the rules that aren't good anymore. So it can be really, really hard to manage these large rule bases and get them to do inference in the correct way, right? So, and there's a couple of minor issues that I won't really touch on, but think about confidence estimation. How certain are we that we're taking the right action? There's like no way to put a number on that. So that's easy then. Let's go to these neural networks. So let's try to simulate how the human brain works. And here I want to also again caution you. This is not something I can just ship you. And I'm going to give you an example why in a minute. So neural networks, they can be very brittle. Now, I stopped playing chess the day I was able to write the computer program that was better than me, that could beat me at chess, right? I decided that if I can write a computer program to do something better than I can do it myself, it's no longer worth it. And it takes me about a day to write a computer program that's better by the neural network that I can train to be better at chess than I am. In fact, the hard job is to simulate the chess game such that I can train the neural network. But still, neural networks struggle to properly drive a car. We stick many neural networks in cars and we train them for millions of miles. And I can assure you, I haven't driven millions of miles. Not to say I'm a good driver, but at least it didn't take millions of miles of driving before I could get out of my driveway. And that is what it takes in traditional autonomous driving systems. Well, why is that? And I'm going to give you a hint. It's because it's an open-ended system. Another example I have here is the image on the right-hand side. Now, if you take a good look, there's 2 images. This was a neural network that was trained to do on-par image classification. On-par, what we mean in neural networks is we mean at least as good as a human operator would do it. This was a 17-layer neural network. I'm sure there was a 23-layer, there was a 6-layer, there was a what have you, and the 17-layer neural network did the best. And on the left-hand side, it does a pretty good job, probably about as good as I could do. So this is a picture of some animal that runs around a grassy field. To classify it as a mammal, a gazelle, possibly a vertebrate, right? All in the sort of the 90th percent confidence, which is about where I would be. Then we introduced the slightest bit of noise. You're probably going to have to put your nose on the computer screen to see the noise that was introduced in the right-hand side image. And the exact same neural network thinks it might be a tree or an ecosystem, or possibly a leaf, but it's not very certain about it. And I can barely tell the difference. Now, you might say, it's like, I'll go and then train that neural network on noisy data. That doesn't work neither, because I can still see what this is if I turn it to black and white, or if the shadow goes the other way, or if I only see half the picture, I can still classify this as probably a gazelle, right? And so neural networks are really brittle. The problem we have in AIOps and applying neural networks and artificial intelligence in the networking space is that it is really hard to predict when it won't do a good job. Now, I cannot ship a product to my customers when I cannot predict when it will work and when it won't work, right? So that's really the key. And so the key here is choosing what algorithms to use where. And just for your entertainment, I put up the taxonomy of machine learning algorithms, right? This is not a black box. There's a lot of different techniques. And what separates the men from the boys is knowing which one to apply where. I'm not going to actually spend any time on that. So to finish out this section, I decided to give you a little bit of an example of that, right? Because, and we'll talk about this more in a little bit, the reasons neural networks don't necessarily do as good as we hope, and that we can't put the finger on when they work and when they fail, is because state is unknown. We just don't know what they latch onto, right? We don't know what they grab as the feature that they find classifying. And therefore, by training into a lab and then shipping it out in the real world to do root cause analysis is actually really hard. So here's what I did. This is just one of 1,000 experiments that we've done in the labs at Riverbed. I grabbed about 2 million NetFlow records. Now, NetFlow is a 5-tuple, and it's got packets and bytes in it. These were actually bidirectional flows. Doesn't really actually matter. And then I went ahead and and this was in a multi-tenant system. In this case, I grabbed flows of 6 different customers. And I went ahead and I trained this neural network on the first half of that data set, and to try to correctly classify which tenant, which customer that the flow belonged to. And then I went ahead and I took the other half of the data set and I just tested, just to see if it could recognize a flow and put it in the right bucket. And my expectation, knowing what I know about neural networks, is this was going to be like all over the place, random. And to my surprise, you see the diagonal, which is mostly green, it actually did really well. And here I was faced with a problem, right? So my hypothesis was that this was going to be a bloodletting for neural networks. But in reality, based on the amount of green, we were getting accuracies in the 75 to 90% range. Now, 75% isn't very good when you're driving a car, not trying to hit a pedestrian, right? Like that's not gonna work. But when you're trying to classify flows, just as an experiment here, I was pretty impressed. Now, the hard part I had was trying to figure out what caused the neural network to specifically latch on to certain flows as opposed to others, right? And in some cases, it turned out to simply be IP blocks. In other cases, it turned out to be port and duration of the flows. And in others, we could very clearly see there was a confusion that was happening simply because of the overlap in similarities. So leaving this behind, right? This is where I'm trying to get to with moving from wrenching and grunt work to becoming the conductor, the orchestrator of my network. And I'm not going to tell you anything you don't already know, but networks and applications have become more complex, right? We're seeing a mix. Every customer I speak with, and I speak with a lot, has a mixture of SaaS applications. We're all using O365, G Suite, what have you, Salesforce, Slack, etc. And we have tons and tons of applications that we're sticking in infrastructure in VPCs, what have you, right? A lot of customers are also still operating data centers. There's work from anywhere. At any one given moment, I don't even know if my cell phone is connecting over Wi-Fi or over LTE. And with 5G, that is going to become even more confusing. SD-WAN, path selection, this was already happening at the BGP level. You can't really quite tell what path your packets are going to take, but SD-WAN has taken that a step further, especially with failovers, path tests, what have you, right? There are lots and lots of additional layers of complexity that give us a lot of benefit, that give us resiliency, that give us availability of networks, but it also makes it much harder for a guy like John to troubleshoot what is really going on. Now, one that I want to really point out is the application interdependency. I've been in I was an incident responder. I've been an application builder, software writer for many years of my life. And one thing that cloud services has brought is it's actually really much easier for me to build applications today, right? I can grab a database that's cloud native. I can put a message bus on top of that. Then I have dashboards that I can download and provision as services. And through Kubernetes, I can load balance that. It's fantastic, right? It works much easier to build applications today than it did in the past. However, I'm creating interdependencies that are super complex, and I can't always quite tell where that interdependency is hurting me. So if I, as an operator, have to know every step of that chain, and I have to understand exactly how the packet moves every time, then yeah, it's going to take longer and longer and longer to troubleshoot and find the issues in performance, but also security in my network. Instead, what I want is I want these AI and ML technologies, some of which I'm going to show you later today, to try to make that operator of the network the conductor, right? I want to put them on top of the food chain so that they are not busy with trivialities, but instead they're busy understanding the network because of the intent that they have for the network. And intent is one thing that AIs and ML technologies cannot have. Intent is something that's unique to humans. Humans understand why the network was built, how it should be operating, and they're able to prioritize which problems are more important and less important. And the best thing I can hope to do, is make them more effective at that. So that's going to be the focus of everything I'm going to tell you today. And at this point, I think we're going to give it back to John.